So in talking about data visualization with Python, I'll start by just making this distinction between the kind of visualization that we do for ourselves when we are doing science and the kind of visualization that we do to communicate with others. And that can be a little bit different. The one about communicating with others also depends on who these others are. A lot of our use cases have to do with writing papers about the science that we do. And then there are sort of considerations about the format and the particulars of the papers. And won't talk much more about that fact, but I think that's an interesting and important distinction. As you're doing science yourself, it's important to build tools that you can use that visualize the things that you need to visualize for yourself. As this is a recurring theme here, probably, is that over the last few years, there's been just an explosion of tools to do data visualization in Python. In fact, there is a website called pyviz.org that I enjoy, and it's dedicated to giving a one-stop shop for just all the different things that are going on in visualizations. And you can see there are all kinds of different things that people are doing, building dashboards, and there are high-level tools and more low-level tools. And this map here comes from this website. Each box here is a library in Python, and you can see that they're divided up into these constellations around major stars. There's the JavaScript world over here on the top right in red is the world in which you want to visualize things in a web browser. A lot of use cases where you do want to visualize things in the web browser. And although JavaScript is a language of its own, and there's a lot of data visualization tools in JavaScript proper, there are also a bunch of libraries in Python, like Plotly, that we'll see a little bit later today, and Bokeh, and all these other libraries around here, where you can write Python that then generates the JavaScript for you, that then goes into the browser, and you can upload into the web, and people can view that. On the bottom right here, in green, is the universe of OpenGL. OpenGL is sort of a set of standards for very high performance visualizations. So these are cases in which you need to visualize a lot of data, often cases where you want to visualize complicated three-dimensional structure with lots of data. And OpenGL, you can write directly in OpenGL, but again, there are Python libraries that allow you to manipulate OpenGL in a way that creates very powerful visualizations. So this is this bottom left corner here. And then on the right here is the universe of Matplotlib. And this is where we'll start our journey today. Matplotlib is a library that's been around for about 20 years and is a library that's a good start for data visualization in Python. And that's because it's relatively easy to get started with. It's relatively straightforward in terms of visualization, and it's probably similar to other tools that you've seen in scientific computing. These other tools on the left here are quite different from scientific computing. This thing on the right is very scientific computing oriented, and oriented towards creating publication quality visualizations, things that you will put into your manuscripts, particularly with an emphasis on two-dimensional visualizations, not the visualization of three-dimensional objects. So let's start with that. So I'll just say Matplotlib, like I said, it's been around for a long time. It was actually started by a neuroscientist, John Hunter, while he was a postdoc at the University of Chicago. He was frustrated with the tools that he was using at the time and started a new tool based on Python. The Python scientific ecosystem was just kind of getting started at that point. But Matplotlib became really one of the cornerstones of that ecosystem. And within a few years, it was very, very popular. At this point, it's a very big community with more than 1,000 contributors. And the library and its visual style has become really familiar through its impact on really major scientific results. The thing I put in here is a figure from the paper that made known the results of the LIGO collaboration. The LIGO collaboration had these two measurement devices, one here in Hanford, Washington, one in Louisiana on this other side of the country. And they recorded the first, this was the first recording of gravitational waves through the collision of two big black holes really, really far away. And that gravitational wave of that collision of these two black holes came to us. And so this figure here is all created using Matplotlib. Another famous visual made with Matplotlib. This picture, I really enjoy this picture. This is also a black hole. In this case, a visualization of a black hole that was created by the Event Horizon Telescope team. And what I enjoy about this picture is that this is a landmark result, of course, but also on the right here, you see the moment when this landmark result showed up on somebody's screen, and the picture on the screen is Matplotlib. It's a Matplotlib window, but also what I enjoy about this is how much Katie Bauman, who led the image processing effort for this result, how much you can see that she's thrilled to see this result show up on her screen. We rarely see this kind of moment. I think it's really cool. Anyway, that said, so, if you use Matplotlib, you're almost guaranteed to make groundbreaking discoveries. So that's great. Let's talk about how to use Matplotlib. So the thing that I'm going to walk you through here is what I will call the one true API. Matplotlib is a really complicated and big library, and there are many ways that you can get in and manipulate graphics with Matplotlib at various different levels. And I really recommend to use this particular API stands for Application Programming Interface. I really recommend using this Piplot API. You'll see how it lets you, on the one hand, gives you a lot of control, and on the other hand, it's just at the right level for you to, it's high level enough where you don't need to manipulate individual lines. Instead, you have pretty strong flexibility, but also expressivity. So in order to get that API, we run import matplotlib.pyplot as PLT. In Python, you can import a particular submodule like this one, giving it any name that you'd like, but this PLT is actually a pretty strong convention. So you'll see this in a lot of code that uses Matplotlib and this API. So I recommend using that. There's one function that will serve as our entry point into this API almost always, and that's this function, PLT.subplots. What PLT.subplots does is that it returns to you two elements. The first element is always an object called a figure object. And the second element is either a single axes object or several axes object. We'll see how that, the multiplicity later. For now, if you call it without anything inside the parentheses, just like that, the default behavior is to give you one figure object and one axes object. And so the way to think about this is that the figure is sort of like the page on which the visualizations will appear, and the axes provide a coordinate frame for the visualization. So in this case, if we do nothing else, we get a coordinate frame which is Cartesian axes going from 0 to 1 and from 0 to 1, and this is the coordinate frame into which now we're going to enter the markings that constitute our visualization. Let's see this in action down here. The axes themselves, because they provide the coordinate frame, they also provide the methods for drawing into this coordinate frame. And so one of them, the most powerful and standard usages of this is a function called plot. Plot takes either a sequence or several sequences and does exactly that, plots them. So in this case, if you provide just one sequence, it will implicitly assume that the x coordinates are 0, 1, 2, 3, and so on, matched to the length of this sequence, and it will assume that this sequence provides the y coordinates for the markings. And the default behavior is to draw a line plot that crosses through the combination of x's and y's, the x's being 0, 1, 2, 3, and so on, and the y's being the values inside of this sequence. So that's what we see right here. Now, if we provide two sequences to plot, then it will assume that the first is the x coordinates and the second one is the y coordinates. You'll notice here I've imported NumPy, and I'm providing instead, here I've provided a Python list, and Matplotlib is perfectly happy taking a Python list. It is also perfectly happy taking NumPy arrays in. So here we're plotting NumPy arrays against each other. I guess I could demonstrate that it's using both sets of coordinates by setting them to be the same thing. And now you see that it's a straight line.
Question.
Yeah.
If in this case you'd use lists, would that have also worked?
Mm-hmm. Yes. You could provide lists here as well. Let's just do that. Yeah, it does the same thing. So it's happy to take any kind of sequence here. And you'll see it does it. The next thing that I'll show you is that it also plays nicely with pandas data structures. It knows about pandas and how to handle pandas, which gives us a little bit more power.
Are there cases where it might prefer NumPy over lists and stuff?
Say that again, please.
Are there cases where it might prefer NumPy functions over?
Yeah, I'll show an example of a case where NumPy might be preferable, and that's, for example, if your y. If you have one y, but maybe you have a two-dimensional NumPy array. So here I've generated a NumPy array that has 2 rows and 1, 2, 5 columns, and that did not work well. But actually it's 5 and 2, 5. Oh, I need to do this the other way around. I need to transpose this thing for the axes to match. And then it draws 2 lines instead of just 1. So in this case, it's nice to have, in many cases, I'll go the other way around. In many cases, you have data structures that have multiple, that should generate multiple lines, that have multiple channels, multiple voxels, multiple things. And then you'd like to plot all of them against one set of x values, the time points in which this was recorded, the TRs in which these were recorded, for example. And then it makes sense to give a NumPy array rather than sequences. Did that answer your question? Okay, what other questions do people have at this point?
Yeah, so kind of following up on that, I was wondering how you can use pandas data frames. Like, would you select columns here?
Let me go into that because that's the next thing.
Okay, great. Sorry.
Yeah. So yeah. So pandas is a very useful data container for these kinds of data sets, and it gives a little bit more. It gives us a little bit more tools for manipulating the data. So often it makes sense to put data in pandas data frames, and then we'd like to plot them using Matplotlib and retain some of the interesting features of the pandas data frame. What I'll do here is I'll read in a pandas data set, a data set, a neuroimaging data set. If you attended the machine learning tutorial earlier this week, you have seen this data set already. It's the Abide2 data set. It has measurements for more than 1,000 individuals. Abide is a big project that aggregated together data sets all dedicated to understanding the neurological basis of autism. So some of the participants, about half of the participants, were diagnosed with autism, and half are controls that were not diagnosed with autism. And the table that we have inside of this tab separated values file here contains about 1,000 rows, each row corresponding to a single subject. And it contains, I think, something more than 1,000 different columns of this data has been processed with FreeSurfer, and FreeSurfer generates different statistics, the area of different ROIs, the cortical thickness, the volume of different ROIs, and something called the gyrification index for different ROIs. So for each one of something like 360, I think, ROIs, we have 4 different metrics. And so this is what the head of this table looks like. Each row here, here we have only the first 5 rows, and then you have multiple columns. You can see there's sort of this ellipsis in the middle to tell us that there's a lot more columns here. And then there are a few of these phenotypical or metadata items for every subject: the age, the sex, the group to which they belong, where if they're diagnosed with autism, group is 1, and if not, then 2. This is a very nice data set if you're interested in kind of like an analysis-ready data set for your hackathon project, this could actually be a really great starting point, because it's already been processed. It's kind of ready to go for analysis. Okay, so what I'm going to do now next is select from among this table using pandas. I'm going to select only left hemisphere regions of interest and only areas that start with the letter V, as in visual, and have a number after that. So the visual areas are numbered V1, V2, V3, and so on. So if I do this selection, I get mostly, I believe I get mostly visual areas. And we can calculate, so this filter operation filters on the columns using a regular expression. This is a regular expression that selects only V and a number after it. So I can drop a few other V region of interest that are not visual areas. And then in pandas, this syntax means take the mean in every column. So I'll get out of that the mean across these more than 1,000 subjects of the area of the visual areas. Yes, the surface area of the visual areas. And what this does is it generates what's called a pandas series object. So this is a series object. This is area, I believe this is millimeters squared area. You see V1, V6, V2, V3, V4, and so on, different Vs. This one I'm not sure is a visual area, but apart from that, the other ones I'm pretty sure are visual areas. So that's good. What we'll do is we'll take this series object that we've created here, and we'll pass that into the plotting command, x.plot. So here I am creating a figure and an axis, and I'm passing this series object as it is into the plot command. And so what's nice about this is that Matplotlib understands that this is a pandas series object, and it understands that this column here on the left, which is called the index column of the series, is something that labels each item. And so it automatically puts on the x-axis ticks the values of the values that are stored in the index with each of the values, and then the y-axis here are the values of that are stored. I should say I'll comment out a few things because I've added some nice additional things in here to show you what this looks like when you run this strictly like that. So one thing that happens here is that Matplotlib doesn't know how long the tick labels are, and so in order to make the tick labels legible and not run into each other, we can call a tick params function that is in the axis. And in this case, we're calling it on the x-axis, and we're applying a change to the label rotation parameter. So tick params lets us manipulate the parameters of the ticks. So that's the thing that rotates it around. And now one more thing that I'll point out is that for every set of axes that you're generating, you should always add the axis labels. And so in Matplotlib, that's done. You do that manually. It won't infer for you what these values are. Instead, you need to explicitly say, I want the x-axis to be labeled as the visual area, and I want the y-axis to be labeled as area in millimeters squared. It's always a good idea to add units when that's relevant. You'll notice that I'm using this notation, dollar notation. And that means that things that are enclosed by these $2 get rendered using LaTeX. So that means that this caret here sets the next character to be a superscript, and we get the nice rendered units here as millimeters squared. So this all together generates, a figure that makes a lot of sense already, right? We see the values of these different things. V1 is big, V2 is smaller, V6 is much smaller, and so on. We can look at this and it already makes scientific sense. And if we were to use this to communicate to others, the fact that we've added X label and Y label really make this much more communicative. This is kind of like the minimal figure might give somebody else if you want to tell them something about this data. Okay.
Question.
Yes.
What if you wanted to organize it by V1, V2, V3, V4? Would you have to go into the data and change that around?
Yeah, you'd have to make sure that the order of this thing is the right one.
Got it.
So I guess you could do something like sort. Index, and then now it's sorting it by these values.
Mhm.
So now it's more sensible.
Yeah.
I think, does it do in place? I think we need to do in place to make sure that it does that in the variable itself. And then now you see it's been reordered.
Got it.
Yeah, it's now, so now we have V1, V2, V3A, V3B, and then V3 shows up here, and that's because of just string sorting in Python. But yeah, you would have to reorder this variable here, mean area, to get the right ordering here as well. It plots it by the order that was given. As I've shown you before, we can plot more than one line into an axis object by repeating the call, well, either by giving it a two-dimensional thing or by repeating the call to ax.plot. For example, let's pull out the mean area of the visual areas in the right hemisphere as well. And here what I've done is I've done the same thing using, instead of left, right here. And then, I'm going to undo this sorting because otherwise things will be confusing. So I've unsorted this back to the unsorted version of this. And now what I'm doing here is I'm calling plot twice. And if I call plot twice, it does generate two lines in here. I've added some more things in here as well. So one thing to notice is that instead of passing, as I've passed here, the full series, I'm passing only the values within the series. That is so that implicitly, Matplotlib thinks that this goes into the same part of the plot as the first line. If I don't do that, I get something like this. It says, oh, I've got these new series of ticks, let me put it over here. And so that's not as useful maybe. And so now we know that the visual areas are ordered in the same way in these two series. And so we can say, oh, well, let's reuse the ticks for the left hemisphere and implicitly say, yeah, that's also for the right hemisphere. One more thing that I've done here is, and I think also provides additional information if you're using this to communicate, is I've labeled the lines. I've labeled left hemisphere for the left one, right hemisphere for the right one. I've rotated the ticks as before, set the axis labels. And then in the end, I've added to the axis a legend. So this makes this box appear. The labels by themselves, labeling the lines by itself doesn't make the axis, labeling the lines by themselves don't make the legend appear. It is only when I call ax.legend that legend appears. And so now we have, again, the figure contains more data. There's the two hemispheres, and it communicates more clearly about what it is that we're looking at. Okay, one more sort of feature of this that we might want to tweak is that at this point, the lines are continuous. That's the default behavior of the plot command, but this data is not continuous. These are sort of categorical, nominal labels, not really continuous labels, and the data was not sampled. It looks like there's some data in between. For example, V1 and V6, there's something in between here because of this line that interpolates between them. And that's a little bit misleading. And in data of this sort, we might want to improve this presentation to give us a sense of where exactly the data was measured, what here is interpolated, and so on. And so I'm going to add a little bit more to the commands that you've seen before. It's basically this cell down here is a copy of this cell, but with some additional information. And that's just to show you that the plot command itself has a lot more options. You can set the markers that you're using. You can set the line style that you're using. Per default, the line style is a continuous line, and there are no markers. But if we add markers, for example, here I'm adding the star marker. Here I'm adding the O marker, lowercase o. When I do that, I get markers at the points at which there are data. I've also changed the line style from a continuous line style to a dashed line style. So dash dash makes it dashed, and that communicates that this is not really data, it's just interpolated. I think you can do line style equals empty string, at which point you get no lines in between. And maybe for this kind of data, no line actually makes more sense. It depends a little bit on what the message should be here. This is more real to the data. And so now this is really communicative already. So I should say there's a lot more things you can do inside of a call to plot, but I won't go into that. And so I'll tell you to go to the documentation and look those things up. But let's see, what questions do you have about this general structure? So this is already gives you a lot of power to do a lot. One more kind of plot that I'll point out. So I'll mention plot is not the only command that Axe is able to execute. There are several different methods for drawing. And the next one that I'll show you is what's called a scatter plot. For example, if we notice that here the right hemisphere V1 is the mean of the right hemisphere is slightly larger than the left hemisphere area, we might be curious about that. And this is not really a statistical comparison, it's just an observation. So we'd like to maybe probe that a little bit more. One way to probe that is to break out from the mean to the individual measurements. And one really good way to make comparisons is called a scatter plot. So here's a scatter plot. What I've plotted here is the column of the area of V1, left V1 against the column of the area of right V1. So every point here is an individual row in the table. I've taken these two columns out and I use one as the x-axis and the other as the y-axis. And I've labeled them accordingly. So left V1 area is down here, right V1 area is up here. And you can see that this creates this kind of scatter plot. And first thing to notice is that it looks like the values are related to each other. People who have big left V1s have big right V1s, and they probably have big heads too, and so on. But just based on this visualization, it's actually hard to answer the question I was wondering about here, which one is bigger? So we need to do something with this visualization to improve it in order to make it a comparison. We'll do a few things. One thing is there's a lot of points here in the middle, and it's hard to say where those points are concentrated. So we'll make the points slightly transparent. The other thing that we'll do is we'll add a line in y equals x, the identity line. This is really helpful in making comparisons because you can see if the cloud of points is above or below that line. And then third, we will set the aspect ratio of this plot so that the x-axis and the y-axis have the same extent and the same length. So here, that's what I'm doing in this cell here. I'm again scatter plotting. So I should say I called scatter instead of plot, which was what created these different points. Sorry, I didn't really pause on that, but I called a different method here, and that's why it appeared as points, not as a line plot. So I do that again, and here I'm setting alpha equals 0.1. What that does is add a bit of transparency to each point, as in it takes away some of the opacity. This is a number that will go between 0 and 1, where 1 is completely opaque and 0 is completely transparent. Given the number of dots here, setting 0.1 makes sense, and you can see that it de-emphasizes points that are out there, kind of the outliers that are by themselves, and emphasizes the large bulk of the points that are here in the middle of this cloud. And also based on this visualization, I also add a line that goes from x at 950 and 5500 to 950. Sorry, the x values go from 950 to 950, and the y values go from 5500 to 5500. No, wrong. X goes from 950 to 5500. Y goes from 950 to 5500. Anyway, it's the y equals x line here. I've colored it black, so here I can specify the color that I'd like, and I set it to be a dashed line. So this is the equality line. And when I set this equality line, it also enforces that the x-axis and y-axis extent is the same, because this goes beyond the extent of the data. And finally, I've set the aspect ratio to be equal so that this and that take up the same space on the page. And so now this really facilitates the comparison that I was interested in. And yeah, it looks like maybe this cloud of dots is slightly above the equality, suggesting that this is a reliable comparison, although I haven't done any statistics here yet, but it clarifies quite a bit. Okay. One more thing. So, okay, so we've created a little bit of a language to look at a particular comparison. One really powerful idea from the theory of visualization that was first identified by Edward Tufte. Edward Tufte is a statistician. He wrote a lot of books. I think he's written like 5 or 6 books about data visualization. And they're really great books in that they really specify very explicitly the criteria for creating good data visualizations. One notion that he came up with is the notion of small multiples. The idea is I've created a visualization here that compares V1 to V1, and now we have this little language for talking about this comparison. We can translate that to multiple different visual areas. And once you've seen one of these, you've seen different ones. It facilitates the comparison between different conditions, between different categories. So what we're going to do is we're going to expand the use of subplots to add more small multiples into the data. And now you'll see the full syntax of subplots, or the addition of this syntax to subplots. If you give subplots numbers here, it will create an array of subplots, or array of little axis objects. And the first number is the number of rows. The second number is the number of columns. So when I call this, I get this kind of array of subplots on the page. And this now, the object X that I've allocated here is now a NumPy array rather than a single axis. And so I can do things like X 0, 0, and that is this subplot here on the left. So I can do like, let me just demonstrate this before we go into a more elaborate example. Plot 1, 2, 2, 3, and that adds a line here into this one. X 1, 2 dot scan or plot 2, 4, 8 will add a line to this one, right? So I use indexing here, like I'm indexing into an array. I am in fact indexing into an array to refer to different parts of this. Okay, how do we use this in creating small multiples? Let's go and insert this into an example that uses the abide data. What I'm going to do here is I have a list of visual areas that I'd like to make this right versus left comparison for. And so I'm iterating over a flat representation of these axes. Here I've created an array of axes called axes. And axes.flat is a flat representation, a flattened representation of this. So it has 6 items in a row. So I can iterate over those items, and in each item, I'm going to read out a different area. I started an iterator here, or an indexer here called II. I take the first area here, and I read out X and Y from the abide table, where here, this format here, what it does is it inserts the name of the ROI. For example, in the first iteration, it'll insert V1 here. So we'll get V1 left, V1 right. On the second iteration, we'll get V2. And then I'm using the scatter plot that I created before to compare those two to each other. I do some additional automation here. I find the smallest value of any value here, either the X or the Y, the smallest value of area that is in this plot. I find the largest value of area in this plot, and I use that in order to plot the equality line. So my equality line goes from the smallest value to the largest value in the data set. And that's because, in contrast to up here, I don't know what to put in here. A priori, I don't know what values should be here. So I read those from the data so that I can automate this. And then I set the labels. Again, the labels are set to be dependent on the data that I'm reading right now. And I finally set the aspect to equal like I did before, so that I get a nice square figure. And that gives me this kind of presentation. There's one more set of things that I do here in the end, and that's to make everything nice. I manipulate properties of the figure, the page on which this is displayed. One thing that I do is I set the size of this so that the aspect ratio of the page, not of every individual, but the aspect ratio of the page is such that these are equally spaced. And then one more thing that I do here is I set the figure to have what's called a tight layout, and that's so that that's needed because otherwise all these things run into each other a little bit, right? You get this overlap between things. Setting a tight layout tells Matplotlib, look, there's a lot of stuff in here. Space it out so that none of the text overlaps with any of the figures. And so you get this full display, and you can see this is kind of interesting. You see all kinds of features. For example, V4 has maybe the opposite. V4 even more consistently has a larger left V4 than right V4 in this area, in this data set, and sort of which areas. So having created one visualization that establishes the language for this set of visualizations, we can look through these and make comparisons across, within. And this is this idea of small multiples. Is one you see probably a lot in scientific literature, and one that Tufte sort of defined as a best practice for visualization. Let me show all this and then just pause here and see what questions do people have at this point. Okay. Oh, I see hands up. Sorry, I didn't see that until now. Hedvig, go ahead.
Hi, so this might be more of a technical question related to Jupyter, but how do we save these plots outside of the notebook?
Yeah, let me show you that real quick here. So this is, again, it's controlled via the figure object. Sort of, you want to save the page, and you can give it a file name that you'd like to use for that. For example, my figure.png, and it will. Let me refresh here. There it is, my figure.png. In Jupyter, you can download that somewhere here.
Yeah, right there.
If I click on that, it'll open it separately in this page, and I think I can save the image as.
Got it. Thank you.
Kai, you have a question?
Yes. Yes. Just to follow up, if I can customize the saved image dimension, the length and width.
Yeah, this is done through this one, so I can do like 26, and then it made it 20 inches wide, and that will go. I can do 20 by 12. It'll look very similar here. Actually, it doesn't look very similar. You can see that we've zoomed out a little bit, but that is controlled through this.
Yeah, thanks.
Yeah, Savannah, what question do you have?
I was just curious if we were going to go over, obviously this is really helpful for like plotting actual data, but are we also going to go over how to create figures that are made from like existing images? Like I see that we have brains in there, but I don't know if that's plotting brain image data onto the brains, or if it's going to also allow us to import like PNGs or something.
Yeah, so I'll skip the statistical visualization part because I'll show a little bit of statistical visualization in a little bit, and I'll skip down here to visualizing images. So yeah, that's one more thing that we'd like to do. Often we do this both as a way to communicate about things, but also something we want to do, for example, when we're doing quality control of our own data. And so Matplotlib, one more thing that Matplotlib allows you to do is visualize images. So here I'm getting some anatomical data. I think it's a template of some sort here. And I create a figure in an axes object, and I use the matShow command in order to show. Here what I've done is I've indexed, I've created a two-dimensional, it's basically one slice into this. And so the color of every pixel here corresponds to the intensity or the values within the voxel in this slice. And I guess I can go up 1 or up 10 here, and it'll give me different things. So that way I can sort of scan through this image and create these kinds of images. I will say, and we'll probably won't get to that, but I also have a notebook here about visualizing things like this, which is a lot more slick. And I'll just say this requires a lot under the hood. And it's all implemented inside of NeLearn, actually, in this case. NeLearn uses a library for 3D visualization called Plotly to do these kinds of things. This is the free surfer average, and on free surfer average, we've placed the Distrio atlas, or they've placed the Distrio atlas parcellation. But you can also add, and NeuroHackademy has lots of examples, you can add statistical maps and other things to these kinds of things. You can display, instead of displaying the free surfer average, maybe you have your individual brain that you'd like to display, not as an inflated, but maybe as a folded brain. I guess I would try this here, Peel. Oh, I don't think this notebook is active. Let's see if Peel works. No, Peel. To get the Peel surface here instead. So yeah, and there's tons of stuff in NeuroHackademy to do those kinds of things for visualizing brains.
I had a follow-up to that. So I was just wondering whether, I was just wondering whether it's possible. So even yesterday in Katerina's brain plot, we couldn't see subcortical regions. I was wondering if that's just something you have to plot separately, or if that's not possible.
Yeah, this kind of visualization is really focused on cortical surfaces. And if you'd like to visualize subcortical stuff, I mean, there are tools where you get little surfaces of each one of the subcortical surfaces, but really because of their nature, they're not, the cortex allows you to sort of, it's topologically a sphere, so you can create this balloon and fold it or unfold it, inflate it as you need, and plot stuff on it. The subcortical stuff just kind of doesn't fit into this picture so well. Let me go back to this and just we're almost at time here. I just wanted to show you one more set of tools that are very, very useful for analyzing things. So you've seen here how you can craft by hand a visualization, maybe small multiples and so on. The next thing that I'd like to tell you is that in some cases, you don't need to do that. You don't need to go and craft by hand every detail of your figure. And that's because for a lot of the kinds of visualizations that we want to make in science, there are a set of repeated steps that everyone would like to do with this kind of data. And fortunately, Michael Wascom, also a neuroscientist, created this library called Seaborn that sits on top of Matplotlib. It uses Matplotlib under the hood, sits on top of it, and creates more expressive kinds of things. The API is a little bit higher level. It takes pandas DataFrames as its input, so I'm importing it as SNS. Again, SNS is a kind of a convention. I'm taking the same abide data, and here I can show you that in one line of code, you can do one of these scatter plots, even setting the alpha along the way. So this is nice, but it's not as useful as, for example, saying, I'd like a much more rich representation of this with more comparisons. And Seaborn contains a set of different kinds of visualizations that are the kinds of visualizations that you typically would want to build out of comparisons. For example, if you're comparing two variables, like the area of V1 and in the left and right hemisphere, it's likely that you'd want something that looks a little bit like this joint plot. So joint plots have a scatter plot in the middle, and then they have these two nice histograms, even with the fitted kernel density estimator in the histograms. To get the full histograms on the X and Y axis, you can very easily, by just adding this keyword argument, not just, but by adding this keyword argument, you get a linear fit also in here. So it fit a linear model here to tell you what the relationship is between these variables, which is something that you often want to know. And then you can control the xlim and ylim right there in the call to join plot. So in one call, you're doing a lot of work. If you were to write this in Matplotlib, this would be a lot of lines of code going into this one thing. Another example of that is, let's say that we're looking at all the variables that come from V1, and this is a regular expression that extracts V1 in the left hemisphere and in the right hemisphere. You can create with one line from the subtables. You just give it data equals V1, and it creates for you this what's called a pair plot, which compares every pair of variables in the data set. On the diagonal, you get the histograms. And notice that it already, because it knows about data frames and knows what this means, it already labels the axes for you. It does the best practices for you. It also the aesthetics are taken care of. Michael has sort of very specific ideas about what things should look like, which is usually pretty nice looking, so it's very elegant. So all the aesthetics are taken care of, and you get these very rich data visualizations, which would require many, many lines of code to create on your own. I'll point to Seaborn's example gallery, which has tons of really pretty visualizations of various kinds, using all kinds of data sets that come together with the software. So as usual, when I create these things, it took me longer to go through the basic stuff, and we didn't get very far here, but there are the notebooks here. They present this idea of tidy data down here, which I won't go into right now, but again, I'll recommend, I'll encourage you to go and look at these notebooks, read through them, and then I gradually introduce more and more high-level APIs, going to next to a library called Altair, which is really high level. So we started from the details in Matplotlib, where you can manipulate individual elements, and you go in the end to these more what's called declarative visualization languages that give the data to some system that generates the right visualization for you based on properties of the data. So that's something to think about, and you can go and see what that looks like in this Altair notebook. This is halfway there with Seaborn. I'd really recommend looking at Seaborn and using it if you're doing statistical visualizations. And then one more step with Altair. And then you also have this one example of brain visualization in the end, because I think that's very useful.